remember Newton's third law, in electrodynamics, it turns out that this law is almost invalid, except possibly in some extremely symmetrical cases, like one we are going to look at here. And here is the Lorentz force for particle 1 and particle 2, and I assumed a certain expression for the magnetic field, which is valid only if v, the velocity, is small. And also, this we are going to use that the electric field is just of the type of Coulomb electric field, and that is valid if the size of the system is small, so we don't have to take into account retarded action here, that it takes some time for the force to and interactions to react here. So anyway, here are the Lorentz forces, and the symmetrical case is a symmetrical perfect circular orbits with the charge q and negative q, and the negative q is giving an electric field E2 in that direction that the charge 1 is feeling, and this is also giving an electric field which is charge 2 is feeling. No 2 here and 1 there. And let's check if Newton's third law might be valid in this case under those assumptions. So let's look at minus force for particle 2 for this one. So we go here and, okay, introduce minus. So it's plus here and minus here. Yes, okay. And then we use this, that E1 equal E2. So, okay, E2 here and E2 here, right? And then we use, when we come here to V2, that one, yeah, that's negative V1, isn't it? So put in that. And here you have V1, that's negative V2, isn't it? So put in that. And then those minus will just, we can take that out from the vector product, and that will just be 1. So what you have left is actually just the force on particle 1. So in fact, Newton's third law is approximately valid for this symmetrical system. In all other cases, it's not, and you need to take into account electric field, retarded electric field, like expressions like this. Okay, thank you very much.